Hi everyone, my name is Josh Go and I am joined by my brother Sam Go. In this SAT Subject Test Mathematics Level 1 module, we will be going over select topics from the Math 1 exam and also go over 30 sample questions that we picked from sample exams. The types of questions that we chose are according to the breakdown provided by the College Board. The breakdown is as follows. For number and operations, we have 10 to 14%, which will make up 3 questions after we cover that topic. This is followed by algebra and functions, which make up 38 to 42% of the exam, and that corresponds to 12 questions. Geometry and measurement cover 38 to 42% as well, which also makes up 12 questions. And finally, we have data analysis, statistics, and probability, which will make up the final 3 questions, which make up 8 to 12% of the exam. Without further ado, let's begin. Alrighty, let's start our review of number and operations. So first we have PEMDAS, our order of operations. P stands for parentheses. E stands for exponents. This is followed by multiplication or division, whichever one comes first, reading left to right, and it's followed by, same thing, addition and subtraction, whichever comes first, reading left to right. Next, we have prime factorization. That's essentially decomposing a number into its prime factors. This also applies to just regular factorization, where you just decompose a number, but not into its prime factors. Let's say we have 120. Let's try to do the prime factorization of that. We can divide that up into 2 and 60. 60 can be divided up into 2 and 30. 30 can go 2 and 15. 15 can go 3 and 5. So thus our prime factors are 2, 2, 2, 3, and 5. And we can verify that all these are prime numbers. Okay, moving on to complex numbers. Complex numbers are in the form a plus bi. They always have a real part. It could be 0, but it also has an imaginary part. So imaginary numbers are defined as a square root of -1. So this is I to the first power, right? So you'll see there's also I to a certain power in the test. We have I squared, which just gets rid of this square root sign, so we have I squared equals -1. Continuing that pattern, we have I cubed equals -I, and then I to the 4th equals +1. And note that as this cycle keeps going, we can extend these exponents into the other powers. This one would correspond to I to the 5th. This one would correspond to I to the 6th. This one to I to the 7th. This one to I to the 8th. And the same process continues for the higher powers. So we can also graph these complex numbers on a graph. We have our x-axis as our real axis, and we have our y-axis as our imaginary axis. So let's take the example. We'll just make up something in a plus bi form. Let's have 1 plus 2i. So in that case, we move 1 unit to the right on the real axis, 1, and then we move up 2i units on the y-axis. So this is labeled 1i and 2i. So then our point would be here. Moving on. So let's quickly do a refresher of our exponential rules. We have rule 1, where we have a base raised to an exponent times the same base raised to another exponent, and that equals x raised to the addition of both those exponents. Rule 2 is like the opposite of this, where we have a base raised to an exponent divided by the same base raised to a different exponent, and that's the same thing as the base raised to the difference of the exponents. So next we have 1 over the exponent, and that's the same thing as saying the exponent raised to the negative exponent. Rule 4, we have a exponent raised to another power, and that's the same thing as saying it's the base raised to the product, or just multiply, both those powers. Rule 5, we have two numbers raised to a power. And that's the same thing. We can break it down into that first number raised to that power times the second number raised to that power. Rule 6 is our identity type rule. And that's just saying any number raised to the 0 power is 1. And rule 7, we have two numbers that are square rooted. And you can break that down into the square root of the first number times the square root of the second number. Because this is the same thing as saying x, y, both raised to the 1/2 power. And we can refer to rule 5, and that's how we break it down. Okay, moving on to Venn diagrams. I just wanted to cover that if we're given a total, I'll call it T, and we're given a amount B for blue, R for red, and an intersection area of X, that this would be modeled by the total equaling blue plus red minus X. Now, you may be asking, why is it minus X? Well, blue covers this entire portion, including that X, right? And red covers that as well. So we're basically double counting that X portion, right? That intersection area. So we have to remove it once just to account for that. All right, moving on. When we have matrices, we can add them together as long as they have the same dimensions. Let's say I have two 2x2 matrices with numbers A, B, C, D, and we're adding it to that second matrix with numbers E, F, G, and H. Here we just add corresponding numbers. So this first item would be A plus E, and we can do the same for the rest. B plus F, C plus G, and D plus H. When we're multiplying, we can get two situations. The first one is where we're multiplying the matrix just by a number. This is called scalar multiplication. In that case, we just multiply that, that scalar to each of the members. So we get 2A, 2B, 2C, and 2D. Now we can also get the situation where we're multiplying two matrices together. And this is called a dot product. And in this case, for this first item, what that would be is we'd have to look at the, let me change colors here. We have to look at the first row of the first matrix and look at the first column of the second matrix. And this term would have to be A times E plus B times G. And we can do the same thing for, let's say, the second term, or the second item, where we have to look at the first row and the second column. So that would be A times F plus B times H. And we can do the same thing for the last two. I'll just do it really quickly. For this one, we have the second row of the first matrix, and then the first column of the second matrix. So that would be C times E plus D times G. Same thing for that last one. Let me change colors once more to navy. There we go. And that would be that second row of the first matrix times the second column of the second matrix. And that would be C times F plus D times H. Finally, we have something called the determinant. I'll just do it for the 2x2 matrix. When taking the determinant of a 2x2 matrix, we have AD minus CB. So that's when you have a matrix that looks like this. So essentially, we're just multiplying these two terms and subtracting it by these two terms, multiplied together. All right, moving on to sequences. In regards to sequences, we have two types. We have an arithmetic sequence, where it's basically just adding a number to the previous number in the sequence. So it would, let's say we have 1. If we add 2 to that previous number, we get 3, and we can continue. 5, 7, 9. So if adding is for an arithmetic sequence, then multiplying is for a geometric sequence. So that would look like 1, 3, 9, 27. That's what that would look like. And the formulas are right up here. All right, let's get started on our sample questions. For the first question, we have if log base b of 2 equals x and log base b of 3 equals y, what is log base b of 72? Well, we can just restructure this because we know that this is equivalent to saying that it's b to the x equals 2. And this is equivalent to saying b to the y equals 3. And the question is just asking us what is, and we can restructure it to b to the what, let's call it z, equals 72. So to find this, let's factor out 72 because we have these two and because we want these to just find these 2 and 3 terms, right? So let's factor it. 72, we have 2 and 36. 36 can be factored to 2 and 18. 18 can be factored to 2 and 9. And 9 can be factored to 3 and 3. So we see here that we have 2, 2, 2, 3, and 3. And if we multiply it all together, we get 72. And coincidentally, these are our terms that we have here, right? 2's and 3's. So how do we write these terms to get 72? Well, we said that if we multiply them together that we get 72, right? So let's do b to the x plus b to the x times b to the x, sorry, times b to the x, right? Because this is equivalent to 2 times 2 times 2. And we can multiply that to b to the y times b to the y, because that's our 3, b to the y and b to the y. And we know that equals 72. So let's simplify this. We know that when we multiply exponents with the same base together, we just add the exponents, right? So this is b to the 3x plus 2y equals 72. So let's write this out. Let's just convert it back to our log form, right? So log base b of 72 equals 3x plus 2y. And that's our final answer, right? The second question asks, if x is greater than 0 and 2 to the x squared minus 1 times 4 to the x plus 2 equals 8 to the x plus 3, then x equals. So what we can do here is take a look at our terms. We have a exponent with base 2, and I think what we should do is try to make it so that every one of these terms has that as its base, right? So we have here, we can break 4 up into 2 times 2 to the x plus 2. And with our exponential rule, we know that this is equivalent to, let's write this first term out, this is equivalent to 2 to the x plus 2 times 2 to the x plus 2. We just break that down, and we know that equals 8 to the x plus 3. So we can continue by consolidating these values. We know that by multiplying exponents together with the same base, it's the same thing as adding them together, as adding the exponents together. So that's x squared minus 1 plus x plus 2 plus x plus 2 equals 8 to the x plus 3. And we know that we can decompose 8 to the x plus 3 as well, similar to how we did it before. Let's quickly simplify this. X squared This is plus 2x plus 3. Looks like equals. Now we can decompose 8 and try to get into base 2 by saying 8 is equal to 2 times 2 times 2 to the x plus 3. So that's the same as saying 2 to the x plus 3 times 2 to the x plus 3 times 2 to the x plus 3. We can simplify this and just show it in another form, which is, because it's multiplied together, we can add the exponents together, and that's 3x plus 9. Now that we have these equal to each other, we know that this term has to equal this term. So we can set that equal to each other now. X squared plus 2x plus 3 equals 3x plus 9. And now we can just solve for x. So this is the same thing as saying x squared minus x minus 6 equals 0. We can split that up into x minus 3 and x plus 2. And we know that our solutions are x equals 3 and x equals negative 2. And because x has to be greater than 0, we know our answer has to be x equals 3. This question asks, what is the reciprocal of the sum of the reciprocals of 2 and 3? So let's find the sum of the reciprocals of 2 and 3 first, before we take the reciprocal of that. And this is our step 1, this is our step 2. So the sum of the reciprocals of 2 and 3. So the reciprocal of 2 is 1/2. The reciprocal of 3 is 1/3. And now we just take the sum of that. And we have to convert this to our common denominator. So we know 1/2 is equal to 3/6. And we know 1/3 is equal to 2/6. We can do this by multiplying the 1/2 by 3 over 3 and multiplying the 1/3 by 2 over 2. And this gives us 5/6. And now the question asks us for the reciprocal of this number. So all we have to do in step 2, I'll color it red actually. Let's color it red, step 2. So taking the reciprocal of 5/6, we just flip the numerator and the denominator, and that we get 6/5.
All right, so this begins our shift into the algebra and functions topic, which, fair warning right now, very important to know how to use your calculator. It can really save you a lot of time if you know when to use it and when not to use it. Okay, so let's begin. Okay, so we're going to start with a little bit of a review like we did before. First talking about domain range, asymptotes, even and odd functions, and inverse functions. So let's start with domain and range. These are kind of the fundamental building block concepts. Okay, so usually we have a function, okay? Usually takes an input, we'll call it x. We'll call the function f of x some sort of machine, right? And it spits out y. And usually we see this written as y equals f of x, right? Y is some function of x. It operates on x, okay? So what the domain is, okay? The domain is the set of all x's, okay, that are possible. Okay, so sometimes, it might be all real numbers. You can, if you're thinking of a 2D graph, for instance, an XY axis, it might be everything from negative infinity to infinity, but there's some exceptions. We'll see more in the asymptotes below, where a certain number might not be included in the domain. So we'll talk about that in a second. Okay, the range, okay, the range is directly related to that. The range is the set of all y's that are possible, okay, given whatever that function is. It is important to note for a function, okay, there has to be this one-to-one mapping. 1x, okay, we'll call it 1x, will map to one y value only. You cannot have 1x mapped to, you cannot have 1x mapped to two different y values. Yeah, that does not make sense. That would look like this, for instance, right? If this is the xy axis, if you had x equals 2, okay, x equals 2 here, you can't have it map to this point here and this point, two different y values. It's not a function, okay? Now let's talk about asymptotes. There's another example in one of the coming slides for this, but let's pretend we had some function, y equals 1 over x. Very simple, right? 1 over x. Now if you graph that, you'll get something that looks like this. I'll do it in blue. Something like this, okay? And you'll realize x can never be 0, right? It kind of, you see these blue lines kind of going off into the distance, but they never quite touch the y-axis, and same with this line as it keeps going up. Likewise with this line kind of approaching the y-axis, they'll never actually touch. Now here's why, okay? That's what an asymptote is, by the way. This dotted line I'm drawing here at x equals 0, okay? That's an asymptote. Just means the graph kind of starts to approach it, but never quite touches it. Now we can quickly talk about why x equals 0 is an asymptote here. If you plugged in x equals 0 here, you will get y equals 1 over 0, okay? That is an indeterminate form, right? Or actually, more accurately stated, this is undefined. Okay, so I'll bring back my red pen here. This is undefined. Okay, so in that sense, x can be anything else but 0. Okay, so that means in the domain, okay, the domain can be everything but 0. And that's why we have an asymptote there. Okay, so that's just wanted to show what the behavior of when you're excluding something from a domain is, and it ends up in an asymptote just like this. Okay. Now in the top right, we're going to talk about even and odd functions really quickly. Okay. In its most simplest form, okay, an even function is where you take f of x, okay, it will equal f of negative x. Okay. Okay. Now an odd function behaves slightly differently. An odd function is where you take f of negative x, okay, that will equal negative f of x. Okay. Let's just see what these sort of mean. Let's see if we can kind of make sense of them, right? So let's say we had this here, okay, and it was a parabola that looked like this. Okay. Not very well drawn. Let's pretend it was very symmetric. Sorry for that stray line. So in this case, let's say we have, it's just x squared, right? If we have the point 2, we'll have the point 4 up here. And if we have the point negative 2, we'll still have the point 4 up here, right? Because that's just x squared. That's an even function, right? Because f of x, so let's say f of 2 is equal to 4, is the same as f of negative x, or negative 2, right? F of negative 2, and that's still 4. Common property, of course, is just, when you look at it from a graphical standpoint, we have symmetry in the y-axis. So we can kind of note that. Symmetry, y-axis. Okay. An odd function behaves a little bit differently. Okay. So let's do this here, and let's draw a function like this. Okay. This is x cubed. Now, why is this an odd function? Let's mark a couple points again. Let's take that point 2 that we have, right? So 2 will go to 8, because it's 2 cubed. Negative 2 times negative 2 times negative 2 is actually negative 8. That's going to be down here. So that matches the definition here that we have for an odd function. F of negative x, okay, so f of negative 2, let's say x equals 2, f of negative 2 is negative 8, equals negative f of x. F of x, f of 2 is 8, negative 8 equals negative 8. Okay, so that's just the distinction between an even and an odd function. And finally, we move on to what an inverse function is, okay? Inverse function. So I'll kind of draw it in a pictorial fashion first to kind of understand what we're getting at. We drew before this function machine, right? Where you put an x into this function f, and it spits out y. The idea of an inverse function is if you have the y and you want it to get back x, you want to go the other way, you want to invert it, okay? We'll call this one f with a -1 superscript, okay? And here we would plug in the y and get back the x, which is really cool. It's very easy actually to solve for something like this. Let's just say we had y equals, let's say, x squared plus 1, okay? All you have to do is switch the variables. So first switch the variables, x equals y squared plus 1, and then solve for y, okay? So that would be y squared equals x minus 1 and square rooted, okay? Square rooted. That eliminates the 2 and the square root, and we get y equals square root of x plus 1, x minus 1. So let's see if that works really quickly. Let's say I plugged in 2 into here, into x, okay? What would y be? 2 squared is 4 plus 1 is 5, right? So y would equal 5. Let's say now I had 5. Will it get me back to 2 if I use this one here, this y equals square root of x minus 1? Well, so far it's looking good because x minus 1, 5, in our case we're plugging in 5, right? 5 minus 1 is 4, and the square root of 4 is 2, and that gets us back our original answer. So that's what an inverse function is. All right, now we'll have a brief word on composite functions. You might see this in a couple ways, but a composite function is basically taking two functions and somehow putting the output of one into the input of the other. Here's what we mean. You might see it in this way. You might see f of g of x. You might also see f and then this little o g, kind of like that, okay? This is basically saying take the output of g of x, right, and put it into the function f. Let's do a couple quick example here. Right, quick example. Let's say f is equal to, or f of x, we'll say f of x, make it simple, is equal to x plus 1. Now I'll write this next one in green. G of x equals, let's say, x squared. Let's just leave it at that, yeah, x squared. What does this mean now if we said, or if we were being asked, what is f of g of x, okay? Now this tells us we're basically putting the function g of x into, or the output of the function of g of x into the input for f of x, okay? So if we now have f of g of x is x squared, right? That's the answer. It's g of x equals x squared. So we're effectively doing f of x squared equals what? Okay. Well, f of x is x plus 1. That means anytime we see an x, whatever's in this parentheses, right, we replace it in the formula, in the x. So we won't just have x plus 1 here, right? This has to now be put in as an input into the function, so this will be x squared plus 1. So that's all really there is to it for composite functions. It's kind of this pattern matching, okay? Now let's talk about transformations. The best way to do this is to probably just draw a quick graph and show maybe a parabola. Here's a original parabola. Okay, so black, in their black pen is the original parabola. Let's just say that's x squared plus 1, okay? Because it's the vertex here is at plus 1. Now, there's a couple ways to transform or translate these sort of shapes, okay? You can, first of all, you can scale it, and one of the easiest ways to scale it first, okay, is scale by -1. Let's see what that does. If you scale by -1, okay, you will get negative x squared plus 1. That gives us negative x squared minus 1 when you distribute it. That gives us something that looks like this. I'm going to draw it in a dotted fashion. That simply flips it over the x-axis, right? You negate it, the parabola now points downward, or opens up downward, okay, toward the bottom of the page. Okay. We can also translate up or down. Translate up or down, okay, simply by modifying this number. Okay, so instead of x squared plus 1, we can say x squared plus 2, right? X squared plus 2. What happens there? All that does is it moves our y-intercept, okay, to 2. So we're now here. It's the exact same parabola, okay, but shifted 1 unit higher. And it's 1 unit higher because it used to be +1, we're now going to +2. That's a change of 1 unit, right? So that just shifts all the y values basically to our parabola up by 1. That's why the whole parabola moves up by 1. Likewise, you can say -1, right? It'll move down to here. Might move down to here. If you just had an x squared without any constants, it's +0, you just get a parabola that goes through the origin, right? Exact same parabola. Now, the last shift we can do, I'll do this one in blue, is left to right, okay? So what that looks like typically is instead of just the x squared plus 1, that was the original, we can say x minus some constant, we'll say x minus 1 squared plus 1. What this minus 1 does, doesn't shift it to the left, okay? That actually shifts it to the right. So x minus 1 actually shifts it to the right by 1. So we'll take that original black parabola, we'll move it over to 1. This point is now here, and we can draw our parabola as such. Okay, so that shifts it to the right. To shift it left, we simply have to say x plus 1, and that would shift it to here, and the parabola would look like this. So it's getting a little messy, but generally plus and minus will simply change which direction, left or right, up or down. Okay, so there's the 3 basic transformations we should know. Okay, finally here in this slide we'll talk about quadratics. That's a very popular topic you'll see, right? A quadratic equation is typically of this form, of this general form here, right? ax squared plus bx plus c, where a, b, and c are different constants. Now, there's multiple ways to solve for the roots or solve for x, right? To figure out where the graph crosses the x-axis. So if we drew a parabola like this, okay, y equals 0 happens here and here. So the x-axis and the y-axis. And given those, okay, we can solve by factoring the equation, if possible, completing the square, or simply using the quadratic formula here, which is x equals negative b plus or minus, that means there's 2 answers, the square root of b squared minus 4ac all over 2 times a. Now, something very special about this. There's a couple shortcuts that hopefully you won't need to use your calculator for. The thing inside the square root, okay, the stuff in here is called a discriminant. And let me write that out for us here. That's b squared minus 4ac. There's a couple very important things we should know about this discriminant, okay? If b squared minus 4ac is positive, so it's greater than 0, okay, we have 2 real roots. The reason is, if it's greater than 0, you can take the square root of it, and then like we set up here, there's a plus or minus, so it would be negative b plus whatever that square root is, and a negative b minus whatever that square root is. So we'll have 2 different answers, okay? When it equals 0, when b squared minus 4ac equals 0, okay, that's another case, we have 1 real root, and it's a double root, okay? The reason that happens is if you imagine negative b plus or minus the square root of 0, okay, when you add 0 or subtract 0, the square root of 0, you get the same answer. It'll always be, your roots will always be negative b over 2a, right? So that'll be a double root. That's where the parabola just touches the x-axis because there's going to be that double root. Okay, it'll look something like this. I'm kind of drawing it a little sloppy on the side, but it will look just like this. It'll just touch and then come back up. It'll touch it once, but that's a double root, right? Like x squared, for instance. Finally, we have a case where we have b squared minus 4ac is less than 0. It's a negative number, okay? Now, if you recall, when we take a square root of a negative number, we're in this imaginary world, right? It's imaginary numbers, complex numbers. So we'll actually have 2 complex roots. We can just say it's their imaginary roots. Imaginary roots. All right. Great, so let's talk about a couple other things for functions to get us to be a little more solidified and how all these different functions look like. First, we'll talk about lines, or a linear function, right? Okay, if you graph that out, that's very straightforward. It has to look like a line. You go from this point to this point, and boom, there's a line, right? That is simply what a linear function is. You can find the distance by using this distance formula. Okay, so we'll call this point x1, y1, x2, y2 for the coordinates. And you simply plug in this formula to find what is the distance between here and here. Okay. The midpoint can be found in a similar way. You use the x1, y1, x2, y2 coordinates, plug it into this formula. And finally, of course, the slope of the line. The slope of the line is simply its rise over run. If they give you a graph on the exam and it has the grid lines and you can count the boxes, it could be very convenient too. But otherwise, you simply use this formula. You basically count how many you go up, right? Sorry, how many you go up. I'll do this in green. How many you go up and how many you go over, right? And that's the slope of that line. Now, you might be given 2 points like x1, y1, x2, y2, and they might just say, hey, you have these 2 points. What's the equation of the line? In that case, I strongly recommend you use the point slope form. We just said how to find the slope, okay? So you could plug that into m. That's what m is. That's the slope. And with any 2 points, okay, you can use either 0.1 or 0.2. You just need to be consistent. You can plug in y1 and x1, and you will get the equation of the line, right? The reasoning behind this generally kind of falls under this reasoning. If you have any 2 points on a plane, like this one and this one, there's only one line in this 2D plane that can go through both of those points. There's only one line that does it, and it's that one right there that I just drew, okay? That's pretty unique. So basically any 2 points can define a line. Finally, we have the slope-intercept form, which if you rewrite the point-slope form, you can actually get to the slope-intercept form. But it's a little more refined version where you keep the y by itself on this left side. The slope is here again, and b is known as the y-intercept. Okay. The y-intercept, as represented by this graph we have here, is this point right here. Right? This point. That's exactly where the line crosses the y-axis, the y value where the line crosses the y-axis. That's the y-intercept. Okay, let's get to a couple more fun, probably more difficult ones. We have a polynomial function. A polynomial function does not have any variables in the denominator. It's usually in this kind of form, like x to the fourth, plus x to the third, and then x to the second. It's just in decreasing degrees, right? 4, 3, 2, 1, and then some sort of constant, maybe plus c, we'll say. Typically, whatever is the highest order, so we have a 4 here, that tells us at most how many solutions, okay, how many zeros this graph will have, or this function has. Again, the zero or a root, however you'd like to call it, is where the function crosses the x-axis, right? Or, in other words, where the function equals 0. So this case here, we've graphed x to the fourth minus 5x squared plus 4, okay? And this graph looks like a nice W, okay? Common shape for a x to the fourth type of function. And you can see very well here, it crosses 1, 2, 3, 4 times. A rational function, on the other hand, does have variables in the denominator. And you see from here, we cannot simplify this any further. That's just how it's left, right? If you recall from our previous slides, we talked about an asymptote and possibly limiting the domain of a function. This is one of those special cases where we see this in action, right? The denominator here cannot be, x minus 1, that's the denominator. It cannot be equal to 0. Otherwise, we'll have x squared plus 3 over 0, and that's undefined. If you look at the plot that's accompanying this on the right side, you actually see that asymptote. I'm going to draw it in a dotted red line here. That's that right there. The graph, you see them kind of going off to the bottom left and the top right. They never touch that asymptote. They never cross, they never touch that asymptote. They get very, very close, very, very close, but it never truly touches that asymptote, okay? So this is what some rational functions may look like. It might not all look like this, but this is just one example. Okay, let's move on to exponential. Y equals 2 to the x. Y equals 2 to the x is our example here. The difference between a polynomial is that the variable x this time is in the exponent. It's in the exponent, okay? So this basically means as x increases by 1 unit, y is doubling, right? And we can kind of confirm that. You can kind of see that going up and shooting up crazy here. So if we had x equals 1, y equals 2. X equals 2 should double it, y equals 4, and so on. So that's an exponential function, okay? Now, it doesn't have to increase. This is because the depends on this base here, right? If we had 0.5 to the x, you might see a function that looks more like this. It might do an exponential decrease like this, okay? So just keep that in mind, but if you know how to use your calculator, it'll be very quick to know how to visualize these different types of functions. Finally, we have the absolute value, and just to remind ourselves, whatever is inside the brackets here, or these straight bars, the absolute value sign, if it's negative, it gets turned positive, and if it's positive, it stays positive. So this graph we have here is an example. If we didn't have the absolute value bars, it would have looked like this. It's just an x squared shifted down 2 units, right? But absolute value takes everything that crosses below here, so everything below here, and flips it up to the positive y region, right? So I'm going to do this in green. This part here is no longer there. It's going to be shifted to here to be positive, right? And that's what you're seeing, this behavior of this weird kind of W shape. Okay, so with that kind of under our belt, we can start on with our couple of review questions here. If Adam can mow a large yard in 3 hours and Matthew can mow the same yard in 5 hours, when working together, how long will it take in minutes, okay, that's different, hours, minutes, for the 2 boys to mow the yard? So this isn't, of course, not necessarily a direct application to anything that we've done with the functions and the polynomials we've just done, but maybe knowing something with what kind of function this is and how to set the problem up is still very algebraic based, right? So let's think about this question. So let's do this. That's kind of the easiest way that I found to do it first. So we'll kind of write their rates that they work at and some sort of fraction, right? So Adam can do 1 yard, 1 y, we'll say, in 3 hours, okay? Matthew can do the same yard, 1 yard, in 5 hours. And we somehow have to combine the two to see how long it would take. Now, very quickly, just to kind of do a sanity check, if they're working together, it should take fewer hours than each one of them combined, right? Each one of them separately. So them combined should take fewer hours or fewer minutes, fewer time than them doing it separately, right? Because they're helping each other out. So one way we can kind of show this is if we add their rate, so 1 yard to 3 hours plus 1 yard to 5 hours, okay? Now if we add this, do some least common multiples, or make the denominators the same, right? Common denominators, we'll get 8 over 15. That tells us these 2 boys can do 8 yards given 15 hours, okay? That's pretty fair. That's pretty, I think that's pretty self-explanatory. They can do the 8 yards in 15 hours if they do it together. But they're asking us how long will it take in minutes to mow the yard, the 1 yard. We just have to flip this, right? To figure out now how many hours for 1. So 15 hours is for 8 yards, okay? How many for 1 yard, okay? We can even set up a proportion if we wanted to. How many hours for 1 yard? Now, when we do this math out, you solve for x, okay? Get x equals 1.875 hours. They're asking very specifically how many minutes will it take, Okay, we know there's 60 minutes to an hour equals 1 hour. So we'll multiply this by 60. We'll get a final answer of 112.5 minutes for the two boys to complete. Oops, that's not well written. There we go. 112.5 minutes to finish mowing the 1 yard. That's choice B. There's another way to look at this in a more equation type form. Okay, so let's do that very quickly here. We can say the rate of Adam times T, the amount they work to mow the yard, plus the rate of Matthew times the time they use to mow the yard should equal 1 yard, right? And that's because what we did before, at least, when we said, let's do this, when we said the rate of Adam, which was 1/3 of a yard in an hour, times 3, that gets us 1, right? Because it takes him 3 hours to do 1 yard. So if we write it in this form, we can actually get 1/3 T. That's the time they're going to spend together now, okay? How much time are they spending together? Plus 1/5, that's Matthew's rate, times T. It's a rate times time should equal 1 yard, okay? And now it's basically the same thing we just did before. It's this times the time equals 1, okay? And when you solve that, you will also find the time in hours, in this case, is 1.875, and you do the same conversion to get to 112.5. So this is just a different way of notating it, this R times T, R times T. Okay, so this is x squared minus y squared equals x minus y, and x is less than y. What is the average or arithmetic mean of x and y? So this is very interesting to think about, right? So at first glance, we're not really sure what to do. You're trying to find an average. We're thinking maybe they'll give us numbers and different things to do. Let's see if we can do some fancy algebra to try to get an answer out of this, okay? So why don't we divide both sides first by x minus y? Okay. The reason I'm doing this is this is a difference of two squares, x squared minus y squared, right? Difference of two squares. And in a difference of two squares, you can always factor it out as x plus y and x minus y, okay? So let's do that real quick. We have x minus y, or x squared minus y squared, equals x minus y. Divide both sides by x minus y, okay? That gets us, I'm going to factor out the top now, x plus y, x minus y over x minus y equals 1. Okay? And as we've said now, these two are the same, x minus y, those are identical. So we know that x plus y equals 1. Okay, well that's great. That gets us something really good to work with. It does tell us that x is less than y, but here it's not very relevant anymore because if we know that their sum is sum is 1, okay, the average, right, isn't the average just the sum over how many there are, okay? And we're trying to find the average of x and y. There's two numbers, that's how many there are. So it's 1 divided by 2. So our answer is simply 1/2, okay? Now, you could try to use a calculator and try to plug in different values to try to brute force it, but you got to be very careful. Plugging in certain types of numbers might not work, right? If you plugged in 0, for instance, for x and y, you get 0 equals 0, and 0 plus 0 divided by 2 is still 0, and that would have gotten you the wrong answer. So much nicer to be able to do it in this very quick algebraic form to get to 1/2 as the final answer. Okay, if x and y are positive integers and 7x plus 11y equals z, so we're working with 3 variables here, which of the following could be a factor of z? Okay, very interesting question. It really makes us think about how to decompose z, right? What makes up z? And it's a 7x plus 11y, okay? So let's think about how we can do that. Okay, so the first way I'll show you how to do this is the kind of the shortcut, okay? So let's say we have some number n, and we're going to set that equal to x equal to y, or more specifically, x and y are going to be equal to n, okay? So we'll just have 7n plus 11n equals z, okay? And if we combine the two right now, you'll get 7 plus 11 is 18. 18n equals z, okay? And it's basically asking us which of these could be a factor of z. So if we plugged in 5 as n, now 5 is a factor of z. If we plugged in 48 as a factor for n, then 48 is a factor for z. And likewise for 77. So just from that reasoning, we know it's choice E. It can actually be any number. It's kind of a trick question. But we can also do this kind of by this trial and error if we're not very convinced, trial error type thing, right? So we can make a table to figure out just what this might look like. Okay, we'll have x and y, and it'll require you to kind of think about first what kind of numbers you want to put in. Having done this ahead of time, I'll show you kind of which numbers do work very nicely. 2 and 1, 9 and 3, 11 and 7. These are good numbers to use for our work. And remember, we're trying to do a 7x plus 11y. So just to show what that looks like, it's 7 times 2 plus 11 times 1. 7 times 9 plus 11 times 3. 7 times 11 plus 11 times 7. Okay? What is z? So let's just add those up. Let's multiply them out. We have 25, 96, and 154. Okay? Well, looking at this, okay, that factor 1 here, or choice 1, or option 1, that's a factor of 5. That works for this. That is a factor of 25. 48 is half of 96, so that's a factor for 96. 77 is also half of 154, right? So that is a multiple as well. So we can see there are numbers that exist that make these possible factors. Okay, so in this next equation, could be useful to graph it. I'm just looking at kind of first glance. We have a couple functions that we're trying to find a y-intercept of, but we may be able to solve it by hand, okay? So let's read it. If f of x is equal to 3x plus 2, that's linear, and if g of x is 2x plus 3, what is the y-intercept of the line whose equation is g of f of x? So now we got to realize or recognize, okay, recognize that this is a composite or compound function, okay? So let's do it by hand first. Let's see if we can, if that'll be faster. G of f of x, okay? That means we have to put f of x as an input for g. So we're really doing g of, and I'm gonna just put what f of x is here, 3x plus 2. Okay, we're gonna put 3x plus 2. Let me do this actually. I'm gonna put a little dot on top of the x, this x at least, so we know that was from the f equation, right? G is supposed to be 2x plus 3. Okay, this is telling us to put the entire 3x plus 2 into here, into just that one x without the dot in it. Okay, that tells us that's 2 times 3x with the dot plus 2 plus 3. Right? That's what it's saying. Put that as an input, and it goes into x here. Now, the dot there was just to show you that was the dot, the x from the f equation. I'll just remove it now. That was just to show that point. So we now have, when we distribute out, 6x, no more dot for us here, plus 4 plus 3. And if you solve that, you have 6x plus 7. And if you know your lines very well, y equals mx plus b, we have that same form. That b, that 7, is the y-intercept. Our answer choice is D. If you weren't sure or did not remember this equation here, if you graph this equation, now that you've done the composite work, right, you've kind of put it through all these steps, once you have this final equation, you can graph it on your calculator and see where it crosses the y-axis, right, because that is the definition of a y-intercept. Okay, This is a little tough question, involves a little trig, which we haven't really covered too much yet, but we'll have a stab at it. If 0 degrees is less than x is less than 90 degrees, then sine of x, all that to the fourth power basically, cosine fourth x divided by sine x minus cosine x equals. Okay, very interesting question. The trick to solving this is understanding what this top is here, okay? That, again, we can identify as a difference of two squares, okay? Specifically, that's sine squared x, okay? That's sine squared x plus cosine squared x times sine squared x minus cosine squared x, okay? And if you don't believe me, if you do FOIL this out, you will get the same as this top here, right? I'm going to divide all of that. Oh, sorry, very bad division line here. I'm going to divide all of that by what's in the denominator, sine of x minus cosine of x. Well, very interestingly enough, this over here, okay, this over here is also a difference of two squares. Okay, so let's rewrite that. So sine squared x plus cosine squared x, okay, that can be rewritten now as sine of x minus cosine, or plus cosine x, and then sine of x minus cosine of x, right? Difference of two squares, all divided by sine x minus cosine x. Excellent. So now we've sort of simplified things. We can actually eliminate these two. Okay, we can eliminate those two. And now we're just left with sine squared x plus cosine squared x times sine x plus cosine x. Now, again, gets a little tricky here. We've decided to include in the algebra section just because of how to see these different algebraic factoring tricks. But you will have to know this one trig identity, that the sine squared of x plus cosine squared of x is simply 1. That just adds up to 1. Okay, so really we just have 1 times this amount here, sine x plus cosine x. So our answer is simply sine x plus cosine x. That's choice A. Okay, number 9. For what value of k will the equation 5x squared plus 6x plus 3k equals 0 have exactly one solution? This will require us, if we remember, to kind of go back and remember what we did in the quadratic kind of review section we had before. Remember that one solution, that's the double root, okay, double root, happens when b squared minus 4ac, okay, b squared minus 4ac equals 0. If we have it as 0, if you remember that quadratic equation, x equals negative b plus or minus the square root of b squared minus 4ac over 2 times a. Having that inside the square root, again, that's called a discriminant. Having everything in here be 0 will leave us with a root of negative b over 2a, right? Because negative b plus 0 or plus or minus 0 is the same thing as just negative b. There's no influence of that plus or minus 0. So we have a, we have b, we have c. Why don't we just look at it in terms of this equation? We don't have to do the quadratic equation itself. Just skip to the discriminant and see what we can do. So b squared minus 4ac has to be 0. That is the condition for one solution, right? The double root. So let's do that. b is 6, that's 6 squared, minus 4 times a times c. c is the entire thing here. So we're going to say times 3k. We don't know what k is. It wants us to solve for that. Equals 0. Let's move, let's add, I guess, this part over to the right side, right? Do it to both sides here. So we'll now have 36, that's from the 6 squared, equals 60k. Okay, you can convince yourself that 5 times 4 is 20, times 3 is 60, and then we have this extra k lying around. Simply solve for k, divide both sides by 60, okay? And we don't expect you to do this all in your head, these simplifications, but if you can, that's awesome. That gives us, if you use your calculator, if you get it in a decimal form, it's 0.6, okay? But if you get it in a fraction form, you will get 3/5, okay, 3/5. And that is answer choice B. Okay, question 10. Which of the following is the equation of a parabola that passes through the points 0, 3, and 3, 0? Okay. Upon first looking at the choices, okay, we can recall some of the things we learned about the different types of functions. A parabola means there's an x squared term. Its highest order is an x squared. It's a quadratic function. You can already eliminate choice A. The reason for that is its highest order is x to the first, right? It's an order of 1. It's linear. That's not going to be a parabola. We can eliminate choice E. That's a cubic, okay? This one might look something like this. That's not a parabola. Okay. This looks like a parabola. This looks like a parabola. Let's look at choice B real quick. Let's write it in terms of y. So that's y would equal the square root of x squared plus 9. That is not quite a parabola. It's a square root function, so it'll actually look something like this. Okay. It's almost like a sideways parabola, but you can't have this bottom section, otherwise it's not a function anymore. Again, to define a function, right, each x value only has one y value. So this can't be both this and this point at the same time. Right? It doesn't map to those two at the same time. So that can't be the answer either. So really, we're just left with choices C and D. Okay. So to me, the fastest way to do this, or two fast ways to do this, it's kind of your choice, is to simply plug in both points to see if they work. Okay, so we plug in 0, 3 first for answer choice C. Okay, that basically tells us is 3 equal to 0 plus 3, or 0 squared plus 3, and it is. If we plug in 3, 0, let's see if that works as well. So 0, is that equal to 3 squared plus 3? No, it's not. By process of elimination, it's going to be answer choice D, and we can check that. A second way to do this, and I won't show it here, is to simply graph those two parabolas on your calculator, and you can very quickly tell, because they're very easy coordinates, which ones pass through 0, 3, and 3, 0. So D here is our answer. Okay, this is similar to a previous problem we've done. What is the greatest integer, k, for which the equation x squared plus 5x plus k equals 0 has real solutions? Let's remember what that means again. Okay, a real solution, b squared minus 4ac, has to be greater than 0, right? Or actually, the limiting case here is when it equals 0. It's still okay. Once it starts to be less than 0, we're not good. So this is kind of our limiting case. This would give us two solutions. This gives us one real solution, but it's just asking for a real solution, right? The greatest integer, k. So let's do a couple things here. Let's just write out b squared minus 4ac is 0, and plug in. So b here is 5, that's this number. That's 5 squared, minus 4 times a, which is 1, times c, which is k, equals 0. Simply have to solve for k at this point. 5 squared is 25. That equals, and I'm skipping a couple steps here, but it's going to equal 4 times k. All right, so 25 equals 4 times k. If you solve that, or divide 25 by 4, you're not going to get a nice clean number, of course. 25 by 4. Okay, 25 by 4 is 6.25. So that means if we were not limited to integers, if k were 6.25, we're still okay. However, we keep going greater than this, okay? Say we did 7, okay? Say we did 7. If you plugged in 7 into here right now, 5 squared minus 28, 4 times 7 is 28, would give you a negative number. That would not give us a real solution, right? That falls into this other category of b squared minus 4ac is less than 0. So that's not good. We need something that's, or the closest integer when we round down this number, right, to the closest integer. And just by looking at the answer choices, we know that is choice B. Okay. This next problem asks us if f of x is 4x minus 4, what value of x, for what value of x is f of x equal to 4? Well, this is basically asking us if we want this side of the equation to be 4, what do we need x to be? So let's see if we can do it by hand. A calculator is pretty useful too at this point. If you graph it, you will get something that looks like this. Okay, kind of like, looks more like a parabola, interestingly enough. Here's minus 4. And it'll kind of look like this very, very narrow parabola that goes like that, right? And all you really have to do is try to look in your at your graph and try to figure out where exactly this positive 4 is and what that intersects. Now you notice these numbers are very close. It might be hard to see on your calculator. There is functionality on a calculator to see where that point hits. You can use some intersections. You can put in a different line. Let's do it algebraically. Might be easier this way, actually. So we have f of x equals, and I'm going to factor here. I'm going to factor out of 4. That's x to the 4th minus 1. Okay? X to the 4th minus 1. We want this to equal 4. 4 equals 4x to the 4th minus 1. Okay? Well, both sides, we can cancel the 4's. That leaves us as 1 equals x to the 4th minus 1. Add 1 to both sides. That's 2 equals x to the 4th. And now, to solve this out, we simply have to take the 4th root, right? Or basically raise it to the 1/4 exponent. So x will equal 2 to the 1/4, which is also the same as saying taking the 4th root of 2. Okay? Now we can put that in our calculator, so you should be familiar how to do that. Okay? That 2 to the 1/4 will get us approximately 1.189. Okay? And the closest answer choice here, if we round to the nearest tenth, it looks like, is answer choice C. Okay, this one's going to be a pretty simple problem. If f of x equals x squared minus 1, that quantity divided by 3 minus 2x, which of the following numbers is not in the domain of f? We spoke before about asymptotes. Remember that? Okay, an asymptote. And it basically tells us we cannot have this to be undefined. So we're really looking for now. That means, where is it undefined? We got to look at that denominator. Just the denominator. We don't really need to look at the numerator. Just the denominator. That's 3 minus 2x. We cannot have that equal 0. And again, the reason for that is, if it were 0, we'd have an undefined form, right? It would be x squared minus 1 over 0. We cannot have that. So that won't be in the domain. We simply have to solve what would x be such that the denominator does go to 0, and then we have our answer because we're finding what's not in the domain, right? So adding 2x to both sides, we get 3 equals 2x, and very simply x equals 3 over 2, okay? And that brings us to choice E, and that's all. Okay, this one's a little more complicated version of what we just did. If f of x equals x to the 4th minus x squared, and g of x is x to the 3rd minus 3x squared plus 2x, then for all values of x for which g of x does not equal 0, what is this ratio? Now, they said this little bit here about the g of x not equal to 0, just so it doesn't become undefined, as we've done in the previous problems. So let's see what they're trying to make us do here. They're trying to say f of x, which is simply x to the 4th minus x squared, we can just replace it, divided by g of x, let's make this a little straighter line here, a little bit of a straighter line, divided by x cubed minus 3x squared plus 2x. We're basically trying to simplify it, right? And it's going to end up one of these answers here. So let's look at that numerator first, just the numerator. X to the 4th minus x squared, I can pull out an x squared, and I'll have x squared remaining minus 1. That's great. In the denominator, I can take out an x, okay, and I have an x squared minus 3x plus 2 remaining. Okay, you can convince yourself if you distribute, you'll get the same as the denominator and the same as the numerator. Let's move a little further from that. Let's see if we can do any more work, right? Like we can try to factor this, we can try to factor this. So now we get x squared. The top is a difference of 2 squares. That's x plus 1, x minus 1, okay? Divided by, the bottom is x times, let's see if we could factor this. Looks like it's x minus 2, x minus 1. That would get us the minus 3 here and the plus 2 here. Okay, it's pretty much in its simplest form as we can get it. So let's see if we can eliminate anything. Here's an x plus 1, here's an x plus 1. Here's an x squared, so we can eliminate with this x. Okay, That leaves us with x times x plus 1 over x plus 2, right? Just simplifying, or sorry, x minus 2, apologize there, x minus 2. And let's just kind of look at the answer choices, okay? So it's not this one, and it looks much like choice B. All right, and in our final question on the algebra review section, if f of x is the cube root of x plus 5, then subtracted by 3, then f inverse of x is. Okay, so as we said before, the way to solve questions like this, to do an inverse, is we switch x and y and solve for the new y. Okay, so we have f of x, which is y, we'll call it y right now. Y equals the cube root, okay, of x plus 5 minus 3. Let me switch the variables right now. X, so y becomes x, equals the cube root of, and this becomes y, plus 5 minus 3. We now just have to solve for y, okay? So why don't we take the 3 and add it to both sides? I'm going to be thorough here. So we have x plus 3, okay? And that equals the cube root of y plus 5. To remove a cube root, we have to cube this side, which we also have to do on the opposite side. So we have x plus 3 cubed equals y plus 5. And finally, to isolate y, this new y, we simply have x plus 3 cubed minus 5. Okay? And if we match this up with the answer choices, this is answer choice A.
Alrighty, let's start our topic on geometry and measurement. Alright, on the topic of angles, we have a few types. We have vertical angles. And these are angles that, when we have two intersecting lines, are across from one another. These angles that are across from one another are equal. So we have angle A equal to angle A. They're across from one another. Same thing with angle B. They're across from one another. They're equal. Next up, we have corresponding angles. And now when we have corresponding angles, that's when we have two parallel lines, like in the diagram shown, that are cut by a transversal, which is what this line is called. Now, when we do that, corresponding angles are equal. So that's this angle, which is an angle formed by the transversal and line L, and this is the corresponding angle, right? Where that transversal and line M. So these angles correspond to one another, and the same apply to all the other angles that are formed by this transversal and these two parallel lines. Now, next up, we have supplementary angles. And that's when, let's give an example here, when angles add up to 180 degrees. Now, let's take angle B and A here. Angle B plus angle A add up to 180. In the same manner, we have complementary angles. And that's when angles add up to 90 degrees. Moving on to triangles. When we're looking at the sides of the triangle, we have equilateral, isosceles, and scalene. Equilateral means you have all sides equal. Isosceles mean that you have two sides are equal. And scalene means no sides are equal. And we can organize it by angle as well. Acute triangle where all three angles are less than 90. A right triangle where one angle is 90 degrees. And an obtuse triangle where one angle is greater than 90 degrees. We're going to cover right triangle after we do this general topic of triangles. For triangles, some general properties that are good to know. Area is equal to 1/2 base times height. The interior angles sum to 180 degrees. And finally, we have this triangle inequality theorem. Let's do a arbitrary triangle here. A, B, C, where the lengths of two sides, if you sum them together, A plus B, that sum has to be greater than the third side, and this applies to B plus C as well, is greater than A. C plus A is greater than B. And by extension, there's also a lower limit to each one of these sides, which is the difference of the two sides. All right, moving on to right triangles. In right triangles, we have the basic Pythagorean theorem, which is a squared plus b squared equals c squared. In addition to that, you have special right triangles. Now, special right triangles are 30, 60, 90 triangles, which you see here, where the side opposite from the 30 degrees is x, the hypotenuse is 2x, and the side opposite from 60 degrees is x radical 3. In the same way, we have another special right triangle, which is the 45, 45, 90 triangle. So in that case, both legs of the triangle are x, and the hypotenuse is x radical 2. I'd like to quickly go back to the Pythagorean theorem. You also have this thing called Pythagorean triples that you should know. A few good ones to know are 3, 4, 5, and you also have 5, 12, 13 right triangles. So just those are pretty common numbers that some tests use. So that's 3, 4, 5, and 5, 12, 13. So for quadrilaterals, we have rectangles and parallelograms. Rectangles have an area of length times width, and we know that if it's a square, length equals width, so the area of a square is just the side length squared. For parallelograms and rhombi, the area is equal to length times height. Now, we just have to note that when you have a rhombus, all sides are equal in length. For trapezoids, the area equals base 1 plus base 2 over 2 times the height. And the sum of the interior angles sum to 360 degrees. And we're going to cover that here with interior angles. Now, the interior angles of a convex polygon is defined as the number of sides minus 2 times 180. And we can verify this with our triangle where we have 3 sides. 3 minus 2 is 1 times 180, and we know that the interior angles of a triangle is in fact 180. So let's move on to circles. Now circles have a few properties. Area equals pi r squared. Circumference equals 2 pi r. And we should note that 2r is the diameter. So we can also say that the circumference is pi d. The full circle covers 360 degrees. And the standard equation for a circle is x minus h squared plus y minus k squared equals r squared, with h and k being the coordinates of that center point and r being the radius. Another few parts of the circle that we have to note is arc. Now this arc is defined as a fraction of the angle that it makes over 360 times the circumference. Now why is that? We're taking the fraction of the circle, and we're multiplying that by the total length of the circumference. So we can do this, we can extend that same thing to the area of the sector, the area of this slice of the pie, right? Where we just take the fraction it covers and multiply it by the total area. A few more notes that I like to cover. A tangent line to a circle is parallel to the radius. And we also have inscribed angles. This one's slightly more in depth, but you have a angle inside a circle, and these are called chords. And a cool special property is that the angle this makes, no matter where it is inside this circle, is actually equal to half this angle that's created when we connect these two to the center point. All right, moving on. So on the topic of volume, you have a few of these on your reference sheet, but I wouldn't really rely on them because there's so little of them. They give you the volume of a sphere, cone, and pyramid, and also the surface area of a sphere. But I advise to just memorize them, right? The volume of a cone is 1/3 pi r squared h. The surface area, I don't think you really have to remember, but it's 1/2 CL. with c as a circumference and L as a slant height. The volume of a sphere is 4/3 pi r cubed. The surface area of a sphere is 4 pi r squared. And the volume of a pyramid is 1/3 base times height, with base being the area of the base. So if they give you length times width for that, that's what you should do. All right, so moving on to rectangular prisms. You have a volume of length times width times height, and you have an area of 2 times the sum of length times width plus width times height plus length times height. And finally, for a right cylinder, you have a volume of pi r squared h with an area, a surface area of 2 pi r times r plus h. This essentially just breaks down the cylinder into 2 circles and a rectangle. All right, moving on to trig. For trig, the most important mnemonic to use is SOHCAHTOA. This tells us that the sine of an angle is equal to opposite over hypotenuse. The cosine of an angle is equal to adjacent over hypotenuse. The tangent of an angle is equal to opposite over adjacent. And that's for this, you can just refer to this right triangle over here. Now we also have a special property in trig where we have sine squared theta plus cosine squared theta equals 1. In addition to that, we also have the law of sines, where for any triangle, we'll call this side A, this side B, and this side C, and we'll call the angles opposite to each of them, the capital letter of their side names. So we know that in the law of sines that A over sine of angle A equals B over sine of angle B equals C over the sine of angle C. Another rule that is less important in this exam, but is still good to know, is the law of cosines. So again, with any triangle, we have, so let's refer to this diagram that I drew up here, c squared, the length of c squared, equals a squared plus b squared minus 2 times the length of a times the length of b times cosine of angle c. All right, let's get started on the sample questions. This question asks, what is the equation of the line that is tangent to the circle whose center is at 0, 2, and whose radius is 5 at the point 3, 6? All right, let's take a look at this. If it says the center is at 0, 2, and that's right here, and the tangent line crosses 3, 6, 1, 2, 3. Let's just draw that here, so that with the circle, we can go up 1, 2, 3, 4, 5. So this is like the radius. So it goes like somewhere like that at that area, and the tangent line goes like that, right at this point. So remember, one property we said about the tangent line to a circle is that it's always perpendicular to the radius. So just by creating a line connecting the point and the center, that will be our radius. So because it's perpendicular, we know that the tangent line has to have its slope as the negative reciprocal. Let me just write that here. If we're doing perpendicular, negative reciprocal of the slope of the radius line, right? So let's quickly find the slope. We have the 2 points, so we can just do rise over run. Rise is, we have 6 minus 2, which is 4. Run, which is 3 minus 0, is 3. That's our slope of our radius. Slope of radius. Now, because we're trying to find the negative reciprocal of that, what we actually have to do is flip it and put a negative sign before it. So negative 3/4 is our slope of our tangent line. Now, looking at the answer choices, we don't have to do any more work, right? Because this eliminates all of these answers and just leaves us with E, with our slope here because it's in y equals mx plus b form. And we don't even have to find our y-intercept at that point. All right, if f of x equals absolute value of x plus 1 and g of x equals x squared minus 5, which of the following is the graph of y equals f of g of x? Well, this is one of those composite or compound functions, right? So all we have to do is just take this value and just plug it in to the x value here, right? So let's write that out. F of g of x equals the absolute value of x squared minus 5, right? This is our g of x, plus 1. And this would be what we're trying to find in these graphs down here. Now we can simply either just graph this out on our calculator and just do it that way, or we can just do it by inspection here. All right, let's quickly simplify this to absolute value of x squared minus 4. So we know that it's going to be a parabola, but it's going to be shifted down from this point. This is going to be x squared, right? Hold on a sec. Let's call this the graph of x squared. And now all we have to do is just shift this graph down 4. I'm going to draw this in green, so this is going to be down 4. So because it's an absolute value, all the negative values are going to be flipped over the x-axis because they're absolute valued. So the graph that looks most closely resembles this would be answer choice B. And you can graph it on your calculator even to verify this. This question asks us for the area of rhombus ABCD if AB equals 10 and the measure of angle A is 45 degrees. So let's draw that out. A, B, C, D at our vertex, and AB equals 10. We know that this is a rhombus, so all sides equal 10. And it tells us the angle A is 45. So to find the area of a rhombus, we need the height, right? So that's this value here. And this creates a right triangle. And now you must be thinking to yourself, oh, we could use trig. Yes, we can. But we could also do a sneaky trick because we know that this has to be a 45, 45, 90 right triangle. And remember, I'm just going to refer back to what we covered in previous slides. And we covered that in a 45, 45, 90 right triangle, again, this rhombus is not to scale because this definitely doesn't look like 45 degrees. 45 and 45. That we have x on both legs and x radical 2 as our hypotenuse. So here we have the length of our hypotenuse. It's 10. So 10 equals our x radical 2. So by dividing both sides by radical 2, we're going to get our leg, which is this length over here, which is our height. So doing that on your calculator, 10 divided by the square root of 2, we get x equals 7.07 something, right? But we need to multiply this by 10 to get our area, which is 70.71 something. So this looks like answer choice C. This question asks for how many integer values of x can 6, 8, and x be the lengths of the three sides of a triangle. Now, you should be recalling our triangle inequality theorem, or like that third side theorem, where the sum of two sides has to be greater than the length of the third side. So then in this case, 6 plus 8 is greater than x. And we can also say that 8 plus x is greater than 6. In addition, we can say that 6 plus x is greater than 8, right? All right, so this means that 14 is greater than x. Now you may be hasty and say it's 13, right? Because those values would satisfy this inequality. However, we also have to know that there's a lower bound to this x value. And let's take this equation to highlight it. If we subtract 6 from both sides, we know that x has to be greater than 8 minus 6. Now, let's simplify that. X has to be greater than 2. So that gives us our lower bound. Let's combine our two inequalities, and we get 14 is greater than x is greater than 2. That tells us we can cover values 3 all the way to 13. And how many values is that? That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's 11 values. Therefore, our answer is D. In the figure above, in this case it's below, the length of each edge of the cube is 2, so all the edges are the same length. If P, Q, R, and S are the centers of the faces ABFE, BCGF, DCGH, and ADHE respectively, what is the perimeter of quadrilateral PQRS? All right, so we know that this is in the center of this face, this is the center of this face, this is the center of this face, this is the center of that back face. Okay, and it's asking us for the perimeter. Okay, let's take a look at the bird's eye view of this cube. So it's going to look something like this, right? Where each side is of length 2. And it's telling us to find the perimeter of that inside square. In this case, it makes a square. All right, so we know that because it's a cube, all sides are 90 degrees. And we can just, by analyzing and just looking at it in different ways, we can see that, oh wait, this side is 1 for this triangular piece. This side is also 1. Well, with that information, we can actually find the side of that quadrilateral in the center. We know that both of these sides are equal, so it tells us that it's actually a 45, 45, 90 triangle, right? And I'm just drawing it on the side here. We know that if this length is x, this length is x, this length is x rad 2. So that tells us that this length is actually, we can just use our special triangle shortcut and just get this edge as 1 times rad 2, which is just rad 2. And if we just multiply rad 2 by 4 for the 4 sides, so we find the perimeter, we get our answer, B. In a trapezoid, which of the following could be true? The diagonals are congruent, 2 adjacent sides are congruent, 2 adjacent angles are congruent. All right, let's take a closer look. We know that the definition of a trapezoid is that it only has at least one pair of parallel sides, at least being the keyword, meaning all sides could be parallel. It could be like a square, right? Or a rectangle. I'm going to do a square in this case. So this is a really specific case of a trapezoid. The diagonals are congruent inside a square, so we know that this is true. 2 adjacent sides are congruent. That's true too. We have a square. Yep. And finally, we have 2 adjacent angles are congruent. In this case, whether it be a square or a rectangle, adjacent angles are congruent. And even if it was a trapezoid that's symmetrical around its center point, right? Around the center line, these adjacent angles are congruent as well. So all 3 statements are true, because we can find cases where each of those statements are true. In the diagram above, square ABCD is inscribed in a circle. And a circle is inscribed in that square. What is the ratio of the area of the outer circle to the area of the inner circle? All right, so based on the square, we can try to find this length, right? Because this is the radius of the bigger circle. And we can also try to find this length, which is the radius of the smaller circle. Now, these are fairly easy to find. Let's say the length of AB, or all sides of the square, are, let's say they're all 2x. I'm using 2x because that would make this length x, right? You can convince yourself that because this side is also 2x, that 1/2 of that is this length here, and that's x. So the area of a circle is pi r squared. So we're trying to find the ratio of the area of the big circle to the small circle. So let's do the small circle on the bottom. We know that its area is pi x squared. Now, because this is a square, we know that if we do this, if we create this diagonal line here, that this forms a 45, 45, 90 triangle. And doing that, we know that with this special triangle, that with each leg length as x, the hypotenuse length is x radical 2. So this is perfect. We can do the same exact thing because we know that this leg is also x. So we can just do pi times x radical 2 squared. And this simplifies to, we can take out the pi here, cross it out from top and bottom, and get x squared times 2 over x squared. Now we can cancel out 2 and 2. So our ratio is 2 to 1, which is 2. And the figure above shows the graphs of y equals g of x and y equals h of x. What is h of g of 4 minus g of h of 4? All right. So let's assume that each one of these ticks represents 1 unit. So let's quickly find what g of 4 is and what h of 4 is. So g of 4 looks like 1, 2, 3, 4. It's going to be around here, right? So that's y equals 1, 2, 3. So g of 4 equals 3. H of 4. Just draw that down. Draw it here. That's this point there. That's y equals 1, 2, 3, negative 3. So now that we have that, let's plug it in. So h of g of 4 is the same thing as h of 3. And then just copying this over, you have g of h of 4, which is g of negative 3. So let's see what those are. Let's do it in blue. So let's start with h of 3. H of 3 is down here, and that's negative 2. And g of negative 3 is right here, which is positive 1. So negative 2 minus positive 1 equals negative 3. And that is our final answer. This question asks, if f of x equals 7x plus 3 and g of x equals 2x minus 5, which of the following statements must be true? The lines y equals f of g of x and y equals g of f of x are parallel. The lines y equals f of g of x and y equals g of f of x are perpendicular. And or the line y equals f of g of x minus g of f of x is horizontal. All right, let's take a look. It looks like they're just making these into composite functions. So let's try to do f. Let me do this in red. F of g of x first. Let's write that out. We know that g of x is 2x minus 5, so we just plug that in as our x value in f. And that gives us 7 times 2x minus 5 plus 3. Let's simplify. 14x minus 35 plus 3. Simplify. 14x minus 32. All right, let's do our g of f of x. G of f of x. I'm going to do that in blue. So that's the same thing as plugging this f of x value into our x here, right? So that would be 2 times 7x plus 3 minus 5. That multiplies out to 14x plus 6 minus 5, simplifies to 14x plus 1. So we know that these two have the same slope, meaning they are indeed parallel. Perpendicular would mean that if they had if their slopes are negative reciprocals of one another, and that's not true. And if you were to subtract them, let's see what happens. So this is f of g of x. That's 14x minus 32 minus our g of f of x, 14x plus 1. Let's distribute out this, this negative sign. 14x minus 32 minus 14x minus 1. So all that would be is this would cancel out, and we'd get minus 33, right? Equals y, and that would be a horizontal line. So this indeed is true too. So our answer is 1 and 3, E. If in quadrilateral ABCD, the measure of angle A to the ratio of the measure of angle A to the measure of angle B to the measure of angle C to the measure of angle D is the ratio 1 to 1 to 2 to 2, which of the following statements could be true? We know that the interior angles of a quadrilateral, any quadrilateral that's convex, is n minus 2 times 180, right? That was our formula, but we know this to be 360 degrees. So we're just somehow trying to divide 360 degrees into this ratio. So it looks like these sum up to 6, right? 1 plus 1 plus 2 plus 2 is 6. So if we do 360 divided by 6, we get 60. So we know that 1 in the ratio corresponds to 60. Therefore, our actual ratio of angles is 60 degrees to 60 degrees to 120 degrees to 120 degrees. You can verify this by adding it up. It should add up to 360. And with that, what can we do? Let's draw our quadrilateral based on this, right? So if angle A is 60 and angle B is also 60, and these two are 120, what does that look like to you? That looks like a trapezoid, right? So it's definitely going to be, 3 is going to be one of the answer choices. Now, could it be a parallelogram and a rhombus? Well, the sides have to be in the order A, B, C, D, right? If the two 60 degrees are always together, are always adjacent to one another, right? They're always going to be one away from another. It can't be a rhombus or a parallelogram. So therefore, our answer is 3 only. In the figure above, in this case it's below, the ratio of A to B is 3 to 2. So that's defined by this. A to B equals 3 to 2. And we can cross multiply that to get an equation. And we get 3B equals 2A. Then what is the value of A plus B? Now, because this figure is not drawn to scale, I don't want to trust it by doing this line and doing this above it. I don't want to trust that. What I'd rather do is just take the entire circle, right? Because all these add up to 360. So we have 1A, 2A's, 3A's, and 4A's. 4A plus we have 1B, 2B, and 3B plus that 18 degree value equals 360. This we know for sure, right? So if we were to do 360 minus 18, we get 4A plus 3B equals 342. And all we have to do is, we have these two equations now, right? And now we just solve for, it's a system of equations and we can solve. Alrighty. So in this case, it looks like we have 3B up here and 3B down here, so we don't have to do much simplifying here. And we can just simply plug in 2A in there, right? We can just plug in 2A right into there. So 4A plus 2A equals 342. Now this is equivalent to 6A equals 342, and dividing 342 by 6, we get 57. A equals 57 degrees. Alrighty, now let's try to find B. Let's just plug A back into this upper equation here. Because why not? 3B equals 2A. 2A equals 114 equals 3B. divide 114 by 3, and we get b equals 38 degrees. So now the question asks us a plus b, so let's just add both of these together. 38 plus 57 is 95, and that's our final answer. In the figure above, if x equals 110, y equals 40, and z equals 130, what is the value of a plus b plus c? All right, I want to start off with this triangle on the right-hand side. We have b here and c here, and we know this is 40. So we know that these two angles here must add up to 140, because 180 minus 40 is 140. So now we know that with these two angles, they're C and this angle are supplements, B and this angle are supplements, right? So they add up to 180. So we know that all of them, all in all together, add up to 360, because B plus that unknown angle is 180, and then C plus that other unknown angle is 360. So we can have 360 equals B plus C plus their supplements, which we know add up to 140. So subtracting 140 from both sides, we get 220 equals B plus C. Oh, so we've got 2 out of 3 of our final answer. So because B plus C equals 220, this plus this equals 220, we also know that over here that we have these two intersecting lines, so this is a vertical angle, right? 110 goes here. So all we have to do is find this missing angle here and try to translate it to their supplements, and then try to find a from that. Alrighty, so we know the interior angles of any polygon is defined by n minus 2 times 180. Any convex polygon, more specifically. So n is 5 in this case. It's a it's a pentagon in the center. So that's 5 minus 2, that equals 3, times 180, that equals 540 degrees. So we know that that has to equal our 220 that we calculated earlier, which account for this and this. Let me draw that in a different color. Which account for this angle and this angle, right? And we know that this z angle is 130. That covers this angle. We know that this angle is 110 plus 110 plus an unknown number equals 540. Now adding this up, we get 60 at the end. 460 equals 540. 460 plus something equals 540. Now what does that number have to be? It has to be 80, right? So question mark equals 80. Now that we have both 110 and 80, we can do the same thing like we did over here and just try to find their supplements. Well, the supplement of 80, I'm going to draw in green now, is 100. The supplement of 110 is 70. So we know that 70 plus 100 is 170. We know that that plus A has to equal 180. Therefore, angle A is 10 degrees. So we add that to 220, and we get 230. And that's our final answer.
Okay, in this next section, we will be talking about data analysis, statistics, and probability. So let's review a couple of these concepts first, okay? So we'll start in the left box. We're going to talk about mean, median, mode, and range. The mean, okay, the mean is simply the average of the numbers in a data set, okay? And what that looks like is basically the sum of the terms in the data set, sum of all the terms, divided by the number of terms, okay? The median, there's something very important to pay attention to here, is the middle value of a sorted, okay, of a sorted set of data, right? So for instance, if we go, this is an example here, if we have 1, 2, 3, okay, that's sorted, the middle value is 2, okay? Now you might be in a situation where you have something like 1, 2, 3, and 4, and the middle value here is sort of non-existent, right? It is conventional here to take the median as the average of these two numbers, right? So that the rightmost number of this left set here, the rightmost number, and the leftmost number of this right set here, okay? So just to review now here, a mode is simply the value, okay, value that appears the most. Value that appears most in a data set. So this, you could have multiple modes. It might be a multimodal data set. So you might have 1, 1, 1, 2, 3. So that one, the mode is 1. Or you might have something like 1, 1, 1, 2, 2, 2, and 3, in which 1 and 2 are both modes. Okay. And finally, we have a range of a data set. Okay. That's just the difference of the largest value minus the smallest value. Okay, the next thing we're going to review is the inner quartile range. Now, if you remember how to do a box and whisker plot, I'm just going to show this so we can get an idea, right? It usually looks something like this, where let's say you have a median here, okay, and then some min value and some max value. This is the median, we defined that before, and then this is the first quartile and this is the third quartile, okay? The interquartile range then is represented by the length of this box. That's the IQR, okay? I'm going to call it that for short. So in order to find what that is, let's just do an example just to understand what that concept is. So we'll have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. We know there's, if we split it right down here, there will be 5 numbers on the left, 5 on the right, and it's sorted. So the median here is 5.5. Okay, so that's the median, 5.5. Now, when we look at just the left set here, okay, this is the median of that subset. Okay, this is our first quartile. Likewise, on our right subset, 8 is the median of that right subset. That's our third quartile. The interquartile range then, okay, is simply just taking that third quartile and subtracting the first quartile, right? So in our case, we have 8 minus 3 equals 5. So that is our interquartile range. Now, there's also a convention that's often used in mathematics, in which we take that interquartile range, okay, we multiply it by 1.5, okay? So in our case, we'll just kind of follow through with the example. So we'll have 5 times 1.5, which is 7.5, okay? And now I'm going to draw this interquartile range again, this box basically over here, okay? From that first quartile, this is the first quartile, if we go 7.5 in that direction, or the third quartile and go 7.5 in this direction, that will tell us what our range is before we start counting certain data points as outliers, okay? So for instance, our third quartile here was 8, so this was 8 here, plus 7.5 would have given me 15.5. So if I have a data set, if I had, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 20, let's say this was a 20, okay? You can use this IQR times 1.5 rule and going either left or right, okay, to figure out whether that's an outlier or not. And finally, we'll talk about probability on this page, okay? So the most basic definition of it is the probability of something happening, okay, is the number of desired outcomes, okay, so what we want to happen, over the number of total outcomes, okay? So as an example, I'll put very small over here on the side. As an example, if we're rolling a 6-sided die, right, we can get either a 1, 2, 3, 4, 5, or 6. I'm assuming it's fair. And if the question asks, what's the probability if you roll that one die that you get a 6? Well, there's 6 possible outcomes, right? When you roll that die, you can get either a 1, 2, 3, 4, 5, or 6. And the desired outcome is the 6. Okay, so the probability of getting a 6, I'll use this notation here, would simply be 1, because there's only one possible outcome. There's that 1/6 that we want, okay, divided by all total outcomes, which is 6 total outcomes. That's 1/6. So we can extrapolate this a little further. So let's say we have some event A, right? Okay, that's of something happening. For instance, getting a 6 on a dice roll, right? So the probability of A happening, okay, is 1/6 in our case. It equals 1/6. Now, it's also important to know what is the probability of something not happening, right? So we can just say P of not A, okay? And that's simply because probability, you have to add all your outcomes, right? Everything has to add up to 100%, okay? So the probability of not A has to be 1 minus 1/6, or in our case, more generally, 1 minus the probability of A happening, okay? And finally, if we have something, let's say 2 events, okay, what's the probability of A and B happening? As long as they are independent, okay, independent, and mutually exclusive, okay? So what this means, let me finish writing it out and then I'll talk about what this means. This is, you can just do probability of A times the probability of B happening alone, okay? Let's just talk about these terms real quick. Independent means if A happens, okay, it doesn't affect the likelihood of B happening, okay? So whether one happens or not doesn't affect the other. It's sort of independent of each other. Mutually exclusive simply kind of refers to they can't happen together, right? So you can't have, I apologize, this should say, I'm going to add a caret here, this should say not mutually exclusive, right? We want both of them to happen at the same time. So if it were mutually exclusive, I'll correct myself here, if it were mutually exclusive, A and B cannot simultaneously happen, okay? So for instance, you cannot both be in 9th grade and in 12th grade, right? That's mutually exclusive. What grade you're in is mutually exclusive. So here, the 2 rules that we need to be able to multiply with this formula is that A and B, those 2 events, are independent and not mutually exclusive. And the final topic we'll review before we jump into the last couple review questions are permutations and combinations, okay? So what they basically are is how many ways can something be organized, or how many ways can you group certain things, okay? It's a way of counting really big numbers, okay? They could be small numbers too, but it's very helpful when you have big numbers. So here are the most important things first. Permutation, order matters. Combination, okay? Order does not matter, okay? Let me illustrate this on the side here. Let's say we had 5 kids, okay? 5 kids, A, B, C, D, and E, okay? These are 5 kids. 5 kids. And we want to form teams of 3. This is going to be our kind of the example we'll use for all these different formulas we see here. So we want to form teams of 3, okay? Now, in a permutation, okay, having A, B, and C is not the same as having C, B, and A, okay? So this is more like if you were, let's say, running a race. Let's say these 5 kids were actually running a race, and they were coming in 1st, 2nd, and 3rd place. If A comes first, B comes second, and C comes third, it's not the same as C coming first, B coming second, and A coming third, right? So this is what a permutation is. However, so let's maybe I should kind of write this here. This is a permutation, and order matters. Okay, but now let's say we do a team of 3. Okay, team of 3 people, team member 1, 2, and 3. Is this the same as having, let's say, B, A, C on your team, right? And in effect, it is, right? We're not really trying to distinguish this as the first member. There's no order in how you get chosen on this team. You're going to be a team of 3, and it either has it's ABC on the team, or BAC, or ACB. There's many different ways to write it, CAB, but in effect, that's the same team, okay? So that's the biggest difference with permutations and combinations. So let's just look at these formulas real quick. The number of permutations of n things, so in our case we have 5, right? This is our n. How many things you want to organize, okay, is n factorial. Okay. That basically means if I wanted to organize, let's say, organize these 5 kids, how many ways are there to do it, right? So usually I map it out like this, with multiplication signs in between. And I say, well, in the first spot, I could put any of the 5 kids. That's A or B or C or D or E. Once that first kid is put in, that second slot only has 4 kids left. That third slot will have 3 kids left. That fourth slot will have 2. And the last slot will have 1. Okay? So that's why the formula here is n factorial. Okay? This is a factorial. You just say n factorial is n, right, times n minus 1 times n minus 2 times all the way till you get to 1. And that's what we have here. We're just subtracting 1 each time and multiplying all the way till we get to 1. Okay, so that kind of checks off our first item on the list. Right, in the next one here, the second one, n things taken are at a time. So that is our example of this 5 kids that we have on the right in this first example. In not teams of 3, but in, let's say, first, second, third order of running a race, right? So this notation, we have NPR. That means n things, okay, taken r at a time. How many permutations, okay, how many ways can you do that? Here, remember, order matters. If you take student A, then B, then C, it's different from taking student B, then C, then A, okay? So the way we solve this, you can, if you're familiar with your own calculator, I'm not sure which ones you guys have, but there is functionality on calculators to do these problems, to just kind of plug it into this formula. But the more written out formula we can use is this n factorial over n minus r factorial. And what that means is simply, well, 5 factorial, right? That's what we had up here basically. But you have to correct it. There's a little correction factor because we're only taking r at a time. In our case, we were taking 3 at a time, okay? So that's 5 minus 3 is 2. That's 2 factorial, okay? And when we work this out, we get 60. So there's 60 ways that these 5 students can come in first, second, and third place. All right, and that leaves us with our last one here. The number of combinations of n things taken r at a time is this formula. So it's a little bit different, but almost identical. Let's write it out here. NCR, okay, equals n factorial, looks the same so far, over n minus r factorial with an extra r factorial, okay? Now, why do we need that? Well, like we said, in this example, this illustrative example that we did on the right, ABC in a permutation is not the same as CBA. But in a combination, that's the second one in green now, okay? In this combination, the order of these students does not matter, okay? Given that, we need to remove all the duplicates, right? Because again, if we have ABC, BAC is exactly the same. We have to remove it. There's also BCA, there's CAB, CBA. There's all these different ways to write ABC, right? But in effect, it's all the same. So this correction factor, this r factorial, accounts for that. So when we do the problem now, 5 factorial over 2 factorial, right, times r factorial, and r is 3, okay? So when we do that, we're really just taking 60, which we had before, dividing by 3 factorial, and that number will come out to 10. So there's really only 10, it's very sloppy 10. There's only 10 combinations, basically, that you can make of these 5 kids. Or more specifically, these 5 kids taken 3 at a time. All right, so with that being said, we can start doing a couple of these sample questions before we conclude our review session. All right, so let's get started on the sample question. If a 3-digit number is chosen at random, what is the probability that all 3 digits are prime numbers? Okay, so the first thing we know, let's just kind of understand what the problem is trying to say. It's a 3-digit number, so really I'm going from 100 to 999, right? Because if you go over that, you're at 1,000, that's 4 digits. And if you go below this, you're at 99, right? And that's 2 digits. So we're really just looking within here. It's asking us how many of those numbers, so from 101, 100, 101, 102, all the way to 997, 998, 999. How many of those 900 numbers, if we actually count it, it would be 900 numbers. How many of those numbers, okay, have all 3 digits that are prime? So I would not suggest actually going and counting them. There would be a lot of numbers. Instead, we should do it digit by digit, okay? So we can say something like this, okay? And let's think about what numbers here, how many numbers can we put here that would make it a prime number? How many digits could we put here that would make this a prime number? How many here as a prime number? So as single digit prime numbers, remember 1 is not a prime number. We have 2, 3, 5, and 7. Those are our prime numbers, right? Now, that means we have 4 numbers to choose from here. We'll have 4 numbers to choose from here, and we'll have 4 numbers to choose from here, okay? And to be clear which numbers those are, they're these numbers here, right? So this, this first digit, I'll call it first digit, second digit, and third digit. This can be a 2, 3, 5, or 7, okay? The second one could be 2, 3, 5, or 7, and the last one can be 2, 3, 5, or 7. Let's multiply that out, okay? So 4 times 4 times 4 will tell us how many numbers will have all primes. Okay, so that's 16 times 4 is 64. And now remember, in probability, we want the number of desired outcomes. So I'll just abbreviate that with desired, and number of total outcomes in the denominator. Well, here's our total outcomes. We said there's, out of all the digits, the 3-digit numbers, that's 900 of them. So let's do that, 900, okay? The number of desired, we wanted ones that have only prime numbers, and we've done it in this way here, okay? We're selecting 4, then 4, then 4 numbers, right, from 4 numbers. So that's 64, okay? If we look at our answer choices, that points us directly to choice D. Okay, here's another interesting one. How many 4-digit numbers are there in which the tens digit is 8 and none of the digits is 9? Very interesting. So when it comes to these types of problems, you might as well start mapping out the 4 digits, right? Here's digit 1, 2, 3, and 4. So I'm not going to go through every single possible one. That's a lot of 4-digit numbers. What these are representing is how many can we choose for each slot, okay? So this is how many per slot, or per digit, okay? And then you just multiply them all together. Okay? It's just a very basic kind of multiplication counting principle, right? So the tens digit, that's this one right here. Remember, this is ones, tens, this is hundreds, and we have thousands here, okay? The tens digit has to be an 8. So there's only one number that can go in there. So we'll put it that way. We'll leave that with a 1, okay? None of the digits is 9. Now, let's just remember how many digits we have. We can have a 0, we can have a 1, 2, 3, 4, 5, 6, 7, 8, and 9. They just told us we cannot use a 9 in any of these numbers, in the thousands, hundreds, or ones place. How many does that leave us with for each digit, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I'm seeing is the first number we can choose 9. The first digit we can choose any one of these 9 numbers that we have here that's not crossed out. It doesn't say that you can't reuse a number, right? I could have a 1, a 2, or something, okay? So 9, and the last one could be a 9, okay? There's a little hiccup though, okay? Do we truly have 9 numbers that we can use in the thousands digit? Not quite. you cannot put a 0, right? It'd be weird to write, let's say, the number 0, 189, right? That's, I'm sorry, you can't use 9, 188, right? We don't usually put that 0 up there, so that's not really one of the digits. We should subtract 1 then, and make it, or enforce this fact that we can't also have a 0, can't be a 9, can't be a 0, we'll only have 8 numbers to choose from, okay? So working that out, we simply have 8 times 9 times 9, and of course the times 1 in there. That gives us an answer of 648, which brings us to answer choice D. Okay, so in this final question, we're going to talk about a stem and leaf plot. The stem and leaf plot above, or in our case below over here, gives the grades of the students in Mr. Smith's second period math class on the final exam. What percent of the students earn grades greater than 75? Okay, so what this is basically asking, before we even look at that stem and leaf plot, is asking us what is the number of students who got over a 75, okay, not equal to, just greater than, right, greater than, over the total number of, basically, of number of students, or number of exams, right? Each student has one exam. And then we're going to multiply that by 100% to get a percentage. Now, this is how we're going to read the stem and leaf plot. This is a very popular way of showing data, okay? We look at the legend first, and it says 8 bar 2 represents a grade of 82, right? So this shows us, in this one at least, we know there's a 58, there's a 59, in this one there's a 60, 64, 66, 68, and so on. So I'm not going to do all of them, they'll take quite some time. This is asking us what percent of students earn grades greater than 75. So let's just first count how many students there are. Effectively, I can just count everything on this side, right? Because we said this is a 58, that's a 59. So it's really just how many leaves there are. This here on the left, by the way, probably should have prefaced with this. This is the stem, and these are the leaves on the right side. So let's just do a quick count, okay? So in this first one, there's 2. This one, there's 4 leaves. This one, there's 1, 2, 3, 4, 5, 6, 7, 8 leaves. Okay, and this one, there's 4. This one, there's 1, 2, 3, 4, 5, 6, 7. Okay, now all we have to do is add that up with a calculator, or if you want to do it by hand, that's 2 plus 4 plus 8 plus 4 plus 7. This gives me a total of 25 students. That will be my denominator here. Simple enough. The next thing I have to do is simply find the number of students who got over a 75. Okay, I'll do this in blue now. So this is 75, right? So if I'm going to draw a cutoff over here, this thick blue line, this is a 76, 77, 78, and everything in here, here, and here is now above a 75. Let's just count how many those are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That tells me, okay, 15 students got above a 75. That 15 now, we'll just throw that into the numerator here, right? So now we're looking at 15 divided by 25. 15 divided by 25. That equals 0.6, so expressed as a percentage, that is 60%, leading us to answer choice D. So this concludes our SAT Math 1 review, and we would like to thank you guys for listening and wish you the best of luck on your exam.